Imagine a gymnast on a balance beam or a person walking across uneven terrain. How do they maintain their footing and avoid falling? Just like humans and animals, robots need to sense their orientation and motion to stay upright, especially when moving or interacting with their environment. Without this critical ability, they would simply topple over. The common sensors for robot balance primarily include accelerometers, gyroscopes, and force torque sensors. These instruments work together to provide a robot with a comprehensive understanding of its body's orientation in space, its angular velocity, and the forces it exerts on or receives from the ground or other objects. The fundamental principle behind robotic balance relies on understanding the robot's center of mass relative to its support polygon. An accelerometer measures linear acceleration, telling the robot how fast its velocity is changing in different directions. A gyroscope measures angular velocity, indicating how quickly the robot is rotating around its axes. Together, these form an inertial measurement unit, often called an IMU, which provides crucial data for estimating orientation, a process known as sensor fusion. Force torque sensors, typically placed in feet or joints, detect the ground reaction forces, which are essential for adjusting weight distribution and stepping strategies. For practical applications, robots combine these sensor inputs using sophisticated control algorithms. For instance, a bipedal robot might use IMU data to estimate its lean angle, while its force torque sensors confirm how much weight is on each foot. If the IMU detects a forward lean, the control system might command the robot to take a step forward, or to shift its center of mass backward by adjusting its posture. Advanced techniques like model predictive control anticipate future movements and optimize balance over time, ensuring smoother and more stable locomotion. A key concept in advanced robotic balance is the zero moment point, or ZMP. This theoretical point represents where the resultant ground reaction force acts, effectively indicating the stability margin of the robot. If the ZMP falls outside the robot's support area, the robot will begin to fall. Force torque sensors are directly used to calculate the ZMP, providing real-time feedback that allows the robot to dynamically adjust its posture and foot placement to keep itself stable. Understanding these sensor types and how they are integrated is crucial for designing robots that can navigate complex, unstructured environments with grace and resilience. By continuously monitoring their orientation, angular motion, and interaction forces, robots can effectively predict and counteract imbalances, ultimately enabling them to perform a wide array of tasks from walking on to legs to dexterously manipulating objects without losing their footing.
If you love robotics, like, subscribe, and keep building with us.